Andrew Richard here. Welcome back to the Team Tech Engineering 1315 water filter project. As you know, this will be our final report, and the emphasis of which is on changes that we have made since the testing phase. Here's a little bit of information about the project and some of the changes we made.
First of all, we decided to build the water filtration for this project, and we come up with three media, which is gravel, sand, and charcoal. So on the very first time, we just built the prototype in the bottle of water, and we come up with random ratio of each media, and we run around 1 liter of water, and at the end we can still smell the vinegar, and we have no way to test it just by smelling. And we noticed that the sand and the charcoal media is mixed up together, so that is what we have to fix.
Alright, so for our second run, we decided to start putting the actual pieces together and decided we needed to buy pH strips. Like we said at first, we couldn't test the pH of the water, but there was still clearly vinegar in it. And now our original idea was to stack each media 3 buckets with lids, but we realized that was an issue because when we ran our second attempt, it leaked a lot of water because it was just really hard to perfectly match up those holes. And also from that, sand was getting out of the sand bucket and onto the charcoal.
So on our third attempt, we decided to bring back the cotton that we used initially in the prototype, and we had placed each bucket on top of each other with one t-shirt at the bottom as our source of cotton for media.
So for our final test, we ran water through our filtration system as we had in the past, but this time with the necessary changes we had made. And this time we decided to run all 5 gallons through it at the same time. Like they said, in our final project, we now had the ability to test the pH balance of the water, which we had not had previously. Here are some of the results of that pH testing.
The test strip we got, we just focused on these right here. This is the strip of water itself, no vinegar. This one is the pH strip before and after of the filtration, which have vinegar. So the pH saying that this one is 8.4, before filtration is 6.2, and after filtration is 7.8, which is not really ideally like the water itself, but it's still a very good result.
As you can see from the results of our tests and this accompanying video, in the end, the filter actually worked pretty well. The water ended up being almost completely clear and comparable in pH levels to unfiltered tap water. So all in all, I would say it was pretty successful. Now, Dan is going to tell you a little bit about the volumetric flow rate and the calculations she used to find it.
For the calculation of this experiment, we come up with Darcy equation, which is right here. So K is the cake or media permeability, and which is measure the ability of porous material to allow fluid to flow through. And this is the fluid viscosity. Delta P is the pressure drop across the cake, L is the cake thickness, and Q is the volumetric flow rate of the liquid. A is the area of the cake cross section. If we take a look at this equation in this experiment again, so viscosity is going to be constant because we use the same fluid material throughout the experiment, which is water and vinegar. pressure drop across the cake is also the constant based on one of the reference we read. It's proof that pressure drop is going to be constant. And then the volumetric flow rate of the liquid, we can calculate this by the amount of water used for filtration divided by the time it takes, and the time it takes can measure by the stopwatch method, and the area of the cake, which is also constant because we use the same bucket all the time. So area is pi r squared and r is always constant. So the thing that we need to concern is K and L, and also the Q. So it obviously shows in this equation that the fluid flow rate through the cake is inversely proportional to the cake thickness, which is L. So in another way to say it is the height of each media, the greater of the height, the more time it takes for fluid to flow through it. So one more point we have to take a look again. So if we rewrite the equation this way and assume that A delta P, which is area, and the pressure drop is constant, so in order to make the pressure drop constant, so the Q and the K is the factor that is changing. So if we increase the Q, the K need to be decreased. So in other words, the permeability and the volumetric flow rate is inversely proportional to each other too. Based on this theory that K and Q is inversely proportional to each other, we come up with the idea that because the permeability of sand is greater than gravel, therefore it takes longer for liquid passing through sand than gravel. So based on the experimental data, we prove that this is right. So we use 2.8 inch of sand as in the bucket. This is our water bucket. We will put sand in this bucket, measure the height, and do the same with gravel. So we put 2.8 inch of sand and 3.5 inch of gravel, and we use the same amount of water, which is 1 gallon of water, and we use the stopwatch method to measure the time it takes for 1 gallon of water go through each media. So as we can see, the height of sand is less than gravel. However, the time it takes for 1 gallon of water to go through is longer than gravel. So therefore, based on this experimental data, we can prove our statement that which is it takes longer for liquid passing through sand than gravel. Okay, so this is our data calculation. So you notified that I highlight 3 of this calculation for the volumetric flow rate of all media combined together, and these first 2 we use the compact, and the last one, which is the final project, we use the t-shirt instead. To explain for this one, I have like a sketch of this. So this is our bucket. So this one is gravel, and next is sand, and then is charcoal. So at the very bottom of the charcoal media, we have the hole. So the water coming in can going out from this hole, and then we notice that there's some sand coming out with water still. So we come up with the idea like we're gonna use the cotton pad and cover all of the hole at the bottom of the bucket to solve this problem. So that's why I take note right here is that the first to dry oil with 1 gallon of water and 1.5 gallon of water mixed with 1.5 cup of vinegar and 0.3 cup of dirt are covered by cotton pad. And then, so the volumetric flow rate, which is 9.27 to the negative times 10 to the negative 3 and 9.15 times 10 to the negative 3 liter per second, which is super duper slow. And this does not solve the problem of the sand coming out together with the water. So that's why at the final project instead we use the t-shirt. So for our final project we use 3 buckets. The first one contains gravel, second one contains sand, and the last one contains charcoal, and we put on top of each other, and each bucket we have the whole water coming out. So the change we make, instead of putting cotton pad at the very end of the charcoal layer before the water coming out, we put 1 layer of t-shirt between the sand and the charcoal in order to keep the sand and the charcoal separately, doesn't mix up with each other. And then also we put another t-shirt layer before the water coming out to the final bucket right here. So we double layer of the t-shirt in order to prevent the sand mixed up with the water coming out for the better filtration and for the better volumetric flow rate filtration, because when we use only 1.5 gallon of water, it takes 10 minutes 59 seconds to filtrate, but when we use 5 gallon of water, which is like triple time, it takes only 25 minutes and 37 seconds. Plus there's no sand coming out at the very end. So to talk about the volumetric flow rate, we just take the volume divided by the time, and you can really see the result is much better. For every second, the final project filtration, the filter can filter 0.013 liter of mixed liquid compared to this one, which is only 0.009 liter of mixed liquid is filtered per second.
And now each of us have some final thoughts to share about the project, our successes, our weaknesses, and things we would do differently in the future.
So overall, I don't think we had any significant weaknesses in this project. I think everything went pretty smoothly. We were able to stick to our original design plan for the most part, other than a few slight modifications like the cotton and removing the lids. But yeah, I don't think we had any significant weaknesses.
Throughout the duration of the project, we really found our strengths as a team. We worked really well together. We were each able to contribute our personal skill sets to better us as a team and get the project done on time.
I would say another strength we had is we all, not only do we stick to our original design plan, but we all, like, at first when we assigned team roles, I felt like we stuck to those team roles pretty much throughout the duration, and it worked well. We were able to work well with each other.
So after this filtration project, what we learned and what we can improve in the future is that in the future we use only 1 bucket and separate each layer by actual cloths, and then cover the top with lid instead of pouring water in the bucket manually. we will design another bucket on top of the filtration that is connecting to the filtration and let the water flow by itself. And then we also could design a pump to increase the flow rate. And then we could focus on designing a more safe and clean water containers after the water is filtered and collected. And then we highly suggest and maintain keeping the pH strips to test the pH value of water. And then we also use smaller and more grind jar seed, so more acid will be filtered.
And my final thought is that the water that we filtered tasted very good and that I drank a lot of it. And that's all she wrote. Thanks for keeping up with us. Thanks for checking in. Have a good one. Andrew Richard, signing off.